Okay. In the name of Allah, the most beneficent and the most merciful, Honorable Chief Guest, Professor Dr. Syed Mansoor Sarwar, Vice Chancellor UET Lahore, Honorable Director, Center of Excellence, Professor Dr. Noor Muhammad Khan, Conference Coordinator, Dr. Kaleem Sarwar Sahib, highly learned keynote speakers, presenters, faculty members, participants of the second National Conference on Sustainable Water Resources Management. Assalamu alaikum, Ohayo gozaimasu, Nehao, and good morning. I am highly thankful to the Director Center of Excellence for giving me this opportunity to present some findings of the research as a keynote speaker. Today, the topic of my talk would be monitoring, modeling, and performance evaluation of managed aquifer recharge techniques, which are MAR techniques, for sustainable urban water resources. Dear participants, you know that we human beings, due to population increase, we are, cutting the forests and agricultural areas and converting it into the housing societies, which is called as urbanization. And due to the urbanization, we are disturbing the natural groundwater balance. And as we disturb the natural groundwater balance, so we are in trouble. This would be the sequence of my presentation.
PPT is not moving, sir.
Huh?
PPT moving value. दोबारा share.
PPT यहाँ पे visible है.
Sir, I think now PPT is okay.
Now is okay?
Yes, sir. Now.
Is now slide okay. Is visible?
Yes, yes, sir.
Sorry, I am not hearing. Okay, thank you very much. So this would be the sequence of my presentation. And let us come to the problem statement. As I mentioned you earlier, that we are doing a lot of urbanization. And due to urbanization, what we are doing, we are increasing the impermeable areas, which reduces the infiltration. And on the other hand, to meet the demands of the population, we are extracting groundwater. Due to both reasons, what is happening? The recharge to the ground is reducing, and on the other hand, we are extracting water. So the result is depletion of groundwater table. So as per most of the researchers, their findings tells us that about 1.03 meter is the average depletion groundwater rate for Lahore. And because the groundwater abstraction, it was 0.2 million cubic meter in 1960, whereas now it has reached to 2.45 million cubic meter by 2018, and by now it is further increased. So all previous researchers had showed that the groundwater extraction rate in Lahore is much more greater than the recharge rate. So what is the result? The depletion in the groundwater table. So the modern means to recharge groundwater are rainfall harvesting, making delay action dams, bank infiltration ponds, infiltration galleries, and recharging wells. One of them is the construction of larger diameter recharging wells. UT Lahore, in collaboration with LDA, had installed 4 recharging wells of large diameter. Their diameter was 15 feet and the depth was 30 feet. And later on, we did the monitoring and the modeling for that recharging well. What was its performance through MSc study carried by Masood Ashik in 2020. Then we also carried out one MSc research by proposing infiltration galleries in the model town housing society. And we saw that what is the impact of these infiltration galleries in reducing the groundwater depletion rate. Moreover, over one group of final year projects, they did one study in 2022, and they have explored all the recharging wells. These are installed in Lahore, and particularly what is their health condition. And so this is the total background of these MAR techniques. These are some suitable MAR techniques, which are managed aquifer recharge techniques. One is the ASR, which is the aquifer storage and recovery. Aquifer storage means this is a single well. It is acting as a recharging well, and the water table goes up, whereas the same well, when it is used as a pumping well, the drawdown takes place in the water table. So this is to have a sustainable groundwater extraction, as the groundwater table should not go down. The another technique is ASTR, aquifer storage, transfer, and recovery. So if this is our pumping well, so this is the recharging well, and here through this recharging well, water table is being raised, and then it is transferred to this pumping well, and from where it is pumped. So in this way, this is a sustainable way of keeping the groundwater level. Then the another example is dry well, in which the water table is deeper, and there is a pumping well, and beside that we have installed a recharging well, which raises the water table. The another is the percolation tank. So we may make some weir or obstruction, and we store the surface water that infiltrates into the ground, and on the downstream of that we provide some pumping well. So in that way, so the water table remains almost as the same location, provided that if the recharge rate and the pumping rate, they are same. The next is the recharge to the ground through the rainwater harvesting. And through rainwater harvesting, and what we can do, we can infiltrate into the ground, and the water table will rise. And close to it, we can do the pumping. So in that way, so the groundwater, the resource will remain sustainable. Another is the bank filtration, like this. If there is some canal, river, and on the side of that, if we have a pumping well, then it continuously receives water from this canal, and the water is being pumped, and the groundwater table, the fluctuations won't be much. The another is the dune filtration, and the next is the infiltration pond. Means there is a pond, and the surface water goes inside, and very close to it, we are providing a pumping well for our fulfilling the water demand. So in this way also, what we can do, we can reduce the groundwater depletion rates. And this infiltration pond, in Urdu we call it, or in Punjabi, the Dungi ground. So this is Dungi ground approach. So these are the several approaches which are called as MAR techniques. And one of the MAR technique is providing a large diameter recharging well, which were installed by the LDA in UT Junaid Jamshed Stadium. So this is the Junaid Jamshed Stadium, and these 4 recharging wells were provided. And this is the cross section of the recharging well. The diameter of the recharging well was 15 feet, and the depth of the recharging well was 30 feet, and there were holes were provided, and here the filter was provided. So the inflow, how the inflow goes to the recharging well. So due to the rainfall, once the surface runoff generates, that goes into these pits, and then through these catch pits, the water goes in these sewer lines, and from here, the water goes in sump, and from this sump, the water is supplied through this inlet pipe into the recharging well. So then water is stored in this recharging well, then it moves in the lateral outward direction in all directions, and it recharges the ground. These are the construction stages. This one is the sinking of the well. This is the foundation or pad of the well, and this is the masonry work which was carried out later. These are the ladders provided as the some worker can go down, and this is the filter which was provided around it. Filter material, the coarser material, then the relatively fine material, and the finer material, and this is the top cover of the large diameter recharging well. This is the mini catch pits. This is the design, which is like manholes, and these are the sewer pipes, and this is the grating provided over here. The surface water enters from here, and this is a sump. So it receives water from two directions, and then the water goes to the recharging well. The performance evaluation visually is shown in this slide. So for the rainfall event of July 3rd, 2018, 252 millimeter of the rainfall occurred. And you see this is the annexing ground after the rainfall, and you see that the water is available, a lot of inundation. But here you don't see any flood inundation. The reason is the water immediately entered in these large diameter recharging wells. So large diameter recharging wells are very effective in avoiding the flood inundations and also in recharging the ground, because large amount of water is stored in these wells, and then they keep on infiltrating into the ground. The objectives are mainly for, number one, just to install the flow meter to measure the quantity of the water which is entering in the recharging well, and the installation of piezometers to measure the hydraulic grade line. And the second is assessment of groundwater depletion rate without recharging wells. And the third is to assess the groundwater depletion rate considering recharging wells. And the fourth is to investigate the working condition of recharging wells in Lahore. So this is the methodology of the Masood Ashik, in which he has collected the data, like the daily rainfall data was collected. And in groundwater data, there were water levels, pumping wells, and the recharging wells. And the data was analyzed for temporal distribution of rainfall and groundwater levels, and the depletion rates were computed by computing the average level of the water level using GIS. Then installation of equipment, as two equipments, that the flow meters were installed and also the two piezometers were installed. Then the assessment of groundwater table position using MarFlow without recharging wells and with recharging wells. So without recharging well, the calibration was done from May 1 to 2015 to November 1, 2016. And the validation was done from November 1, 2016 to August 1, 2018. And with recharging well, again, the calibration was done for certain time for which the data was available and the validation was done. And the later on sensitivity analysis were carried out, etc. This was the data which was collected, like topographic data from the Google Earth, the bore log data for the hydraulic conductivity that was from WAPDA and NESPAC, daily precipitation data from PMD Lahore, piezometric data from WASA and UET Lahore, and pumping well data from WASA and UET Lahore. So this is just showing you the arrangement. This whole Junaid Jamshed Stadium was divided in 4 quarters, and it was leveled like that. So the flows, they are going in these 2 sieves through these catch pits, and in this sump, the water first comes, and the sediments and heavy materials, it settles down, and from top it was entering into the recharging well. These are the 2 observation wells, OW2 and OWC2, which were installed by Masood Ashik. So this is the data analysis, which shows the monthly rainfalls for 4 years from 2015 to 2018. And you see the water table variation. When there was more rainfall, so water table level was about 175 meter. And in this year, as there was very less rainfall, as it very little infiltrated into the ground, so the water table was lower to around 168 meters. This is the analysis for the, the piezometric levels in the observation well 2 and observation well C2. And here you can see the levels in the observation well C2 were higher. It means the flow, groundwater flow was from observation well 2 towards observation well 2. And these are the results, spatial distribution of water table in May 2015, and then these are the for August 2018. And here the results are summarized. The average water level in 2015 was 175.35 meter, the average level of the water table, whereas in August 2018, it was 172.94 meter. So which shows that, so average depletion rate was 0.81 meter per year. And this is contour maps of only for the summer season without recharging wells, and this is for 2016, and these are the results for November 2016. And average water level on the May 2016 was 175.39, whereas in November 2016 it was 174 meter. So average depletion rate per season was minus 0.08. So in the summer season, due to more rainfall, instead of the water table going down, it came slightly up with an amount of 0.08 meter. So these are the results for the winter depletion rates without recharging well. This is for 1st November 2016, and this is for 1st May 2017. And you see the average water level changed from 176 meter to 175.14 meter. And the average depletion rate per season was 0.84 meter in the winter. So in the winter, as there is no rainfall, so the depletion rate was, groundwater depletion rate was higher. Here, if you will see the results with recharging wells, and the recharging wells were installed in February. So we have the data February and onward. And you see here that the average water level in the 1st February was 178.3 meter, and they were reached to 178.16 meter by 1st April. And depletion rate for the 2 months were 0.15 meter. Whereas if you will compute depletion rate for the season, winter season, it was 0.45 meter. So the depletion rate in winter, it was reduced due to the recharging wells. Now the installation of equipment, these are the flow meters which were installed. Here, this is the flow meter which was installed close in the one of the sump, and this is the sump, and this hole showing the the flow meter installation. The least count of the flow meter was 0.01 cubic meter, whereas the maximum value was 1 million cubic meter. And this is the installation of the piezometers. So this is the screening or filter pipe, and some filter material was inserted inside, and this was the pad on the top. And the both piezometers were provided with a cap and a lock, as the no one should enter anything inside or temper it. Then the water levels were shifted from the benchmark in UET to the these piezometers. And now this is the modeling for period from 1st May 2015 to 1st August 2018. And this period was divided in 7 stress periods. So the detail of the stress periods is given here. And this is the total modeled area, which is about 1400 meter by 1400 meter. And the cell size was 20 by 20 meter. And the number of columns and rows were 70 and 70. So there were 12 pumping wells which were used for this simulation. 5 wells were in UET and 5 of WASA, which were at boundaries of our area, and 2 of WASA within the model domain. And then, as we know, the duration of the pumping and pumping capacity we know, and from that pumping rates were computed. So these are the calibration parameters which were used in the simulation. So hydraulic conductivity was kept 38 meter per day. That was within the range. A specific storage was 5.3 into 10 raised to power minus 4 per meter, which was within the range. A specific yield 22%, which was within the range for fine to medium sand, and effective porosity 32% and total porosity 38%, all were within the range. The initial head which was given was 174.8 meter. So these are the flow boundary conditions, and varying head was used as flow boundary condition. And these are the model calibration results, which shows that the observed heads and computed heads, they are matching very well. And they are within the very much within the 95% confidence limits. And these are the model validation results from November 2016 to August 2018. And again, you will see that the model can be well validated for the area. These are the contour map of the water table elevation without recharging wells. This is for 1st May 2015, and this is for August 2018. And then there was a modeling with the mod flow considering the recharging well. Again, the total time was divided in 7 stress periods. And the volume of water was calculated by SCS curve number method. And here you can see the 2 events. One was the 2.07 centimeter event, the other was 3.51 centimeter event, and the volume which was used are these.
Sir,
And
sorry to interrupt you.
This was the capacity of the
Sir, sorry to interrupt you.
recharging
Your
well.
time is
Quite high.
10:45.
So it means only 28% of the volume of the recharging well would up. Okay. All right. And these are the results for model calibration with recharging wells, and they are quite good results. And these are the results for model validation, which are within the permissible range. And this is just comparison for these 2 rainfall events, and the how much water table was risen at close to the recharging well. So these are the average findings without recharging wells. The per summer season average groundwater depletion rate was minus 0.72, whereas for winter it was 0.84. But when recharging wells were provided, this depletion rate from here, it was reduced to 0.45 meter. So it means the recharging wells helped us a lot in reducing the groundwater depletion rate. The another case was the infiltration galleries, which are narrow trenches like this, and these are filled with the gravels. And this work was done basically by one student, Fahim Aslam, which was our MSc student, and this model was applied, mod flow was applied to the model town area. Its total area was 592 hectare, and further details of the drainage network are given here. And the infiltration galleries here in blue color are shown, which were provided at the depression points, green belts along roads, sites, parks, parking lots. So total galleries provided were 180, and the total surface area of the infiltration galleries was 4.3 hectare. So these were the locations where the infiltration galleries were provided, and infiltration galleries, they reduced groundwater depletion rate by 0.15 meter. So this is the work done by some of our final year project students, and they have explored that there are 18 recharging wells installed in Lahore by these agencies, and these are the locations where these recharging wells are installed. So it is the summary of their findings. So 4 recharging wells in Junaid Jamshed Stadium of UET Lahore, which is large diameter, and this is the working condition. So if you will see, so there are 4 agencies which have installed these recharging wells, that is the LDA, PCRWR, WWF, and Punjab Irrigation Department. And this is the working condition. So as per present health, out of 18, 9 recharging wells are out of order, they are not working. And these recharging wells are recently installed, maybe around 2017 and so on. So these are the concluding remarks, that the large diameter recharging wells in this study area have reduced the average groundwater depletion rate by 0.39 meter per year, considering winter data, and infiltration galleries in the study area have reduced average groundwater depletion rate by 0.15 meter per year. It means the large diameter recharging wells are more effective in maintaining the depletion of groundwater level. Large diameter recharging wells are more effective in reducing the groundwater depletion rate and flooding on the surfaces due to large capacity of recharging wells. Small diameter recharging wells locally rise the water table and are not much effective in reducing the flooding on the surface. Clogging of the filter material is a serious issue in recharging wells and infiltration galleries. Infiltration ponds, means the deep parks, are the cheapest and the most effective means of groundwater recharge with practically no maintenance cost. So out of 18 recharging wells in Lahore, 9 are found out of order. It means the 50% of the recharging wells we have encountered out of order. So keeping in mind the findings, so these are our recommendations. So large diameter recharging wells are recommended with certain modifications to recharge groundwater and manage flooding. The second, infiltration ponds, means deep grounds, which we call as dungi grounds, are recommended for quick urban flood management and groundwater recharge being most economical solution. So what we recommend, that mix of MAR techniques, large diameter recharging wells, infiltration galleries, and infiltration ponds, dungi grounds. These all should be provided in any new society or existing society to reduce the depletion of groundwater table. Groundwater hydrological studies must be carried out before developing any housing society. and for proposing suitable MAR techniques, and it should be made part of the LDA policy or any city policy. The next is maintenance cost must be added in the project costs for the proper working of the recharging wells. Like 50% of the recharging wells are now not in working condition. So if the maintenance cost is also added in the project cost, so these all recharging wells could have been working now. So with this, I conclude my presentation. So thank you very much for your patience.
Thank you very much, sir, for sharing your valuable